All right, we're about halfway. Ladue High School Chemistry finalist. Okay, here we go. Appreciate all your time on this. All right, balancing equations. The whole key is to get the same number of atoms on both sides. Okay. All right, yeah, I see this. I just kind of go in order. Two irons. Then I'm like, oh, good. You can't. You got to fix, so that's not going to work. So let's try, well, you know what, I could try 4 irons. And then, yeah, some people see that right away. The 3s is 6 and 6, yeah. So really this whole thing, why are we doing this? Why are we making sure we have the same number of atoms on both sides? It's really a fundamental property in any science experiment, is that your energy, your mass is conserved. And so it stays the same on both sides. That is why we aren't destroying atoms, we are keeping them there. All right, so what are we doing here? Oh, types of reactions. This is worth a few minutes to review. Combustion is burning. All right, lighting your Bunsen burner. When you do that, you're burning up anything, usually methane, I guess, and then other stuff. But when it burns, when you react anything, well, organic or combustible material, when you burn it with oxygen in the presence of oxygen, you get carbon dioxide and water. A decomposition reaction, that is really what it means. You take something like a compound, a salt, and it is broken apart. A synthesis is really the same thing. You say, okay, or the opposite, if you will. You take 2 things and you get them to combine. You synthesized something. Now we did a few reactions too throughout the year where you drop metals, just any old metal, drop it into some different acids or salts, some sort of solution-y compound. And then what happens on a lot of the ones, the metal would react and go in with the salt, and then a different metal would come out. In fact, first day of school for a lot of chemistry students was aluminum foil, copper chloride, copper solid, copper metal, and aluminum chloride. Okay, and then really along those same lines, I know my chemistry teacher always told us, well, it's like 2 people go to the prom, and they like to stick together before the prom, and this other couple goes to the prom, and then they go to the dance, and they get googly eyes for the other partner, and they end up swapping. Very 70-ish, I guess she was. So yes, so I think choice D is that is a metal, that is an acid, that is a salt, that is hydrogen. So something is replaced. Good job, choice D. Oh, okay, what was that? I think we just looked at these. So hopefully this is an easy one. That was, please remember, that was what we called a synthesis reaction. Choice E. Very nice, very easy. Don't miss those. Okay. A couple things. This is hydrogen phosphates, potassium hydroxide, potassium phosphate, water. You know, it doesn't jump out at you right away, but if please on these, you can write water as HOH. When you do that, then to me it's easy to see how this is a double replacement reaction, because the hydrogens and the phosphates switched, however you want to look at it. It's really asking you to balance this. So that's the other reason to do that. When you look at the OHs, you can just balance it easier. So, all right, so I got 3 hydrogens. I need 3 hydrogens. I got 1 phosphate, 1 phosphate. Oh, those 3 also affects the OH. So I need 3 of them. Yeah, look at that. Ooh. Okay, so potassium hydroxide, which one is that? Potassium hydroxide is this one. So that was my KOH. Potassium phosphate. Potassium phosphate is that one. So what is my mole ratio? It is 3 to 1. Choice C. Combustion, yeah, we kind of went through that. That was just burning something with carbon, burning it in the presence of oxygen. You're lighting your Bunsen burner, so that's giving off heat. And really, that's, yeah, and really think of this as breathing, please. It's really what cell respiration is. We talk a lot about that in biology. You know, you're giving off water, you're giving off carbon dioxide. Yeah, so that's what you breathe. You breathe out those things. And, you know, yeah, so we said some good examples were cell respiration, breathing. But yeah, just your car. Yeah, that's what I had written down there, your car. You put gasoline in your car, that's a combustion reaction. What's coming out of the back of your car? Water and carbon dioxide as well. Okay. Oh gosh, okay, this looks like double replacement. We got to write down what is coming up. Well, hey, I think words are easier. Lithium and sulfur oxygens is lithium sulfate. PB is peanut butter and lead. NO3s are nitrates. When there's two of those, that is a lead 2. Okay, so that's what I'm mixing up. Lithium sulfate, lead 2 nitrate. Now really, just they switch. So lithium nitrate. And then what's the other thing here? It's going to be lead and sulfate. So once you get that, switching the names, yeah, that's what we got left. Now, oh yeah, they're a little dirty, playing dirty pool again here. But that's okay, we can do this. Lithium nitrate. So lithium, look it up, you're given, please remember you're given charges. Nitrates, just remember the 8s are always the polyatomics. And one of each. My lead sulfate. Well, I guess, like I said, you knew from over there that lead was +2. Another way you know is the sulfates were -2s. So yeah, I drew 1 lead and 1 sulfate. D on that one, it looks like. Okay. Goodness, is this another? Oh yeah. Oh yeah. Okay, so a bunch of stuff. First of all, it is double replacement again, so copper nitrate. Then what else was there? Copper nitrate, silver chloride. Okay, now the question though isn't what do you make, it's what is solid. What is solid in there? So the solid stuff is the stuff that doesn't dissolve. Now we did this with, like, we made yellow, like that real strong yellow dye. We made chalk. We mixed up solutions, salty solutions, and made solids. Those are precipitates. In other words, you could filter them off because they were not in solution. They were not aqueous. So precipitate is same as solid, not dissolved. Now the thing you're given is this chart of what is soluble. So you use the chart, and what does the chart say? It says, when you read those solubility rules, that nitrates are soluble. Nitrates with copper metals are soluble. And the other thing that it says is it says chlorides made of silver are not. If it's not going to be very soluble, it's going to be a precipitate. Okay. Yes, we know that chemical reactions are atoms moving around. It's the conservation of mass. Okay, choice B. Oh gosh, what have we got here? In a reaction. Okay, now please, the whole thing, identify knowns and unknowns. That's what these are all about. So hopefully you can pick out on the question. I got a gram of this stuff. What is that? Oh, hey, this is rocket fuel. Hey, yeah, right. Yes, now they got to really kind of be careful. Remember, give the oxygen tanks a stir. Without the oxygen, you got no fuel. You can't get home. Oh no, Tom Hanks is throwing up in a bag. Okay. Yeah, write down what you're given. Just write it down. Don't even, if you can identify your known, you got it. If you can identify the unknown, you got it. Because then there's no more thinking. Write it down. Drop it down. I don't even think about it. What can I convert those grams to? I can convert those grams to moles. Right? And I just keep going. I'm like, all right. Started with that. And I'm like, all right, I want to keep going. I got mole. I don't know numbers. Grams to mole. Drop it down. Don't even think. Drop it down. And you can always get moles of one chemical to moles of the other. So this is moles of known, moles of unknown. So that is the whole key with this. This is known. This is known. And this is where you make the leap. You go knowns. And then you can change that and figure out, okay, this one here is my unknown. This one here is my unknown. And that's what, once you get there, you're done. You've solved it. Okay, so let's keep going here. Moles, the question wasn't moles. The question up here is grams. But I can do that. I can do that. I can take grams, or I can take moles of unknown to grams of unknown. Okay, now then it's just number time. Okay, a full mole. Gosh, the arithmetic. That's where I get tired. A couple borons. 6 of the hydrogens. Okay, add it together. So a full mole is that. The mole ratio, 1 to 3. Once again, that mole ratio there, 1 to 3. 1 to 3. All right, then, yeah, then you just drop a full mole. Oxygen was 2, couple 6, yeah, O2. Remember the side work. So 2 oxygens, that's where that came from. Yeah, and then please just kind of always remember the calculator. That's a step 2. I get this wrong. That is over 26 times 3 times 32. I get like 3.48 grams of oxygen. That, I believe, is my answer. Running out of colors. Choice C. Okay. Oh, golly. Okay. Oh, this one not too bad because mole to mole. So, if you know moles are 1, you know moles are the other. If your coefficients are the same, your moles are the same, Okay, so mole to mole isn't really bad. This is fair. Okay, so but the whole thing, identify known. You know, identify your unknown. That's tough. That, to me, takes the most time. All right, once I got the known, I don't think. I'm just going to automatic, write it, automatic, mole O2 on bottom. Then I come back to, okay, mole to mole, sulfur trioxide. And then it's just, yeah, mole ratios. They aren't the same, but they're close. But yeah, so what am I doing here? Yeah, it's just basically, I got half, I'm taking 2/3 of half of 2/3, half of 2/3 is 1/3 of a mole. All right, what do we got next? Oh, yes, kind of dirty again. Now, maybe sometimes common sense can kind of help you and save you time. This one's kind of set up. If you're good at these, you kind of recognize 32 grams of hydrogen is a lot more molecules than 32 grams of oxygen. So some people can kind of look at that and be like, that's got to be limiting because that is a lot more. Oxygen's a heavier gas, so that's fewer molecules, so it should be limiting. But let's see here, because we do need twice as much hydrogen. So if you're going to solve this twice, yeah, just don't think. Start there. 32 grams of hydrogen. And then, yeah, then it's just, yeah, okay, I can do this. Grams of hydrogen. Grams of hydrogen. You can change it to moles. Don't think. Drop moles down. This is where you might have to think. Moles of hydrogen have got to get to unknown. Unknown is this. Unknown is water. Okay, still not thinking. Still not thinking. Moles drop down. Yeah, the question though was grams, so I can always get grams. So then I just look at this and I think, okay, a full mole of H2 is 2. The mole ratio is not bad. It is 2 to 2. So those cancel. A full mole of water is 18. 16 plus 2. Yeah, the calculator work. So I would make 288 grams of water. Now below there, you can, if I'm going to use oxygen now, and I don't know, had a few students doing this in class, just saw right away that that was less molecules. So no thinking, no thinking. Just drop it down, change it to moles. Still no thinking, no thinking, drop it down. Have to think, moles of O2 can become moles of the unknown. Moles of the unknown, water, become grams of the unknown. So now a full mole of water was 30. The mole ratio, 2 waters, 1 hydrogen. Full mole of water is still 8. That's the same. If you look, this is the same here. So yeah, how does that look on the calculator? 32 divided by 32 times 2 times 18. And in fact, that is the smaller one. I like that choice. That's a good answer. Okay, this one's not too bad. I think what, excuse me, the confusion oftentimes is people think actual, they think it's true. No, actual just means what you really got. It's what you scraped off your filter paper. It's the best way to think of it. How much could you recover? Sometimes percent yields are called percent recoveries. All right, on paper, we can sit here and watch YouTube videos and predict yields all day. We can do the stoichiometry. We can do that all day. But yeah, this is what. So it's like in theory you should get 100% on a test, but you don't actually get that. Especially if it's a good test, especially if it's a Ladue test. Anyway, okay, so they told us we got 50. We were hoping to get 60. 5/6 is 83 and a third. Very nice. Ooh. Yeah, what do I guess I should maybe make the joke here. I think it's kind of a reoccurring joke throughout the gas videos. Okay. Combined gas law. You know what that is. The thing, yeah, I guess this is what I want to show you with this. If temperature's held constant, what does that mean? Okay, if temperature's constant, it cancels out. But really, that means if your pressure, if you keep that true, if your pressure is going to go down, to keep that true, your volume's going to have to go up. To keep that true, if this goes down, the other one's got to go up to keep that equal. So what do we call that? When P, pressure, and volume, just to keep that true, we call that kind of relationship inverse. And that is a key word with pressure volume, inverse. Yes, pressure versus volume is an inverse relationship. Yeah, I don't know, maybe this is another very, I think, effective way to remember this. Okay, so we had, you guys were pushing. Oh. So you had this thing here, and you would have this, and you could see that as you pushed on this syringe, and there was all these little markings here on it, and as this thing got bigger and bigger, and as you pushed on it, as you made that space inside here, as you kept pushing, oh, it was harder and harder. There was a bigger, more pressure. So that's what I remember. You push on it, you get up here where your pressure's high, you push on it, that corresponds with tiny, tiny little bit of space. As you let it go, let it go, you didn't apply as much pressure. Okay. All right, so yeah, really, the other thing, I don't know, I guess it's worth just a few minutes, real quick. So we said pressure and volume, and we called that inverse. All right. The thing is, if you take pressure and then maybe take the inverse of volume, that looks like that. So if you take the inverse of an inverse, it's called direct. But yeah, really, that's we do a lot of this kind of thing, and I would highly encourage you to take physics. That's really what a lot of students take after chemistry. Okay. Okay. So yeah, this is that same thing. P1, V1, P2. It's just, I think of this as plug and chug, and it's kind of a practice. Kilopascals are pressure, volumes are liters. Okay, so what did we do? We decreased our pressure. Our pressure went down. Went down by a factor of 10. So right away I'm thinking that volume, that unknown new volume, is also going to be going up by a factor of 10. Okay. Yeah, solving, really just get this guy to the other side. And I think you will get a good job solving it there. Okay. Yeah, while I'm solving this, I will say I have my dog in my lap, and he keeps moving. Okay, so yeah, I think that's, yeah, it goes, the volume goes up by a factor of 10, 2 liters. Choice B, very nice. Okay, hope you could still read this. Let me peek at the screen. All right, we're doing good. Okay, sorry. Okay, so the thing to remember here, we did the inverse thing with the pressures. Now let's look at, oh, yes, thank you. One of my favorite days of school. I don't know, one of my favorite movies, one of my favorite foods. But yeah, that is, oh yeah, we also put, we made that. A lot of you guys wanted some salt on it too. And so it was a little tiny thing. We just microwaved it, just heated it up, and it got a lot bigger as we heated it. So the popcorn, as the popcorn got hot, the popcorn got bigger. They both went up. They both go up. Because remember, really what we said, if we take, you know, volume, or, yeah, temperature and volume, whatever, it's direct. It's choice A. Yeah. Really another way, just look at something that is a direct proportion. That's how I think of it, a direct proportion. We say that that relationship to volume and temperature is in fact a direct proportion. So if you can set up a proportion between volume and temperature and it stays the same, stays equal, that is a direct proportion. Yes, please remember, direct proportions not the same as an inverse. All right, and that would be more like volume and pressures. All right, popcorn. Okay, so you can always use this kind of relationship. What do we got here? We're changing a lot of them. Okay, so yeah, just take a minute to define our variables, and then we can do this one too. Here, this will be good. I can still see the screen. Sorry. Okay. Yeah, this is plug and chug. First, pressure. Atmospheres, please recognize those as pressure. That's the whole thing with this, is recognizing your pressure units, because the volume units are liters. Oh yeah, temperatures, and really when you write it in the denominator, and yeah, remember, you're given equations. But yeah, when that shows up in the denominator, I think, oh golly, no negatives, because you can't have a direct proportion with the balloon and popcorn with negatives. And you also can't have zeros. So that's why I remember this temperature here, standard. I think, did it say STP? I'm guessing it did. It looks like STP. Standard is 1 atmosphere. Standard is 0 Celsius. And then, yeah, so our unknown. What's going to happen to this balloon, I guess, or this confined gas in a space when the pressure and temperature change? Please take the time to write it down. Too many people try to do this algebra in their head. I make a mistake. I have to see it. I can't do this in my head. I just have to see it. So take the time to write it down. So how am I going to solve for, yeah, find that V2. I'm going to solve for that. Going to solve for V2 by getting this guy over, getting that guy out. How do I get that guy out? I multiply that on both sides. multiplying that on both sides, punching it all in. Remember, the people that do well can stay a step ahead of this pace. You know, this chemistry final, it's a thing of honor. People talk about it in their graduation speeches. You might even hear about it this weekend. It is tedious arithmetic, and it is good night's sleep, ready to go. It's like an ACT in a way. You just come in and perform. This is a challenge. And like I said, chemistry department keeps records, and they have like people that have gone on to brilliant things to save the world have all started here with the Ladue chemistry final. It is a badge of honor. You should get like a merit badge for this, like a Boy Scout or something. All right. You know, this is another one you're given. This is another one of my favorite equations. It's the ideal gas law, where your number of moles. Your number of moles is your PV over RT. R, that's just, yeah, what is R? R is that gas law constant, okay? And that's, you're given that. We'll do a little bit more with that. But yeah, if you can recognize your pressure was 2 atmospheres, your given volume was 4 liters, that gas law constant, once again, you're given that. Your temperature, remember, I just see it in the denominator. That's my way to remember that the scale has to be adjusted. So it's kelvins. Oh, how did I know 2 atmospheres? Yeah, that was goofy. This was a little tricky. Millimeters of mercury, or the barometer, was invented by the Italian Torricelli. So yeah, double standard pressure is double standard pressure. All right, so yeah, all of that, 0.24, choice D. Okay, yes, keep performing, keep performing. Equations given. Okay, so when I see grams on a gas, I think that that's not very helpful. Grams on a gas, you know, the equations are number of moles. But anyway, okay. Oh, this one was what's true of this amount of gas. So let's look at number 1. Or this is just, this is dirty pool in that it's 3 problems. 1 question, 3 problems. You have to. The only way to pick out the true or false is to do each one. So the first one is how many moles? Well, hopefully that's, okay, 1/4 of a mole, 8 out of 32. Because remember, our oxygen, my favorite, is 2 of them, O2. O2, 32. Then, oh, good gravy. The volume equals, okay, so I know my N, so really, yeah, boom. Gas law constant given standard, oh gosh, so yes, standard ST, standard temp, P, standard pressure. Okay, standard pressure. Wow, that does indeed. It's like, if you knew the answer, why are you asking me? Okay, and then the next one, oh goodness, this is, hey, this was first semester. Doesn't matter. A mole is how many moles? Well, 1/4, gosh, 1/4 of 6.02 times 10 to the 23rd. You couldn't even count 1/4 of them. You don't even breathe in that much O2. Or I should say, you don't even take that many breaths in a lifetime. That's why you can't count that high. There aren't that many seconds. But anyway, okay. So you have a lot of work. Like I said, if you already knew the answer, why did you ask? Okay. All right, 59. Oh, combined gas law. But the way to know kind of how to use it, which is held constant. So on this one, I believe it said P1 is the same as P2. So don't care. Now, So then, yeah, plug and chug some more. Okay, so that first volume, hopefully, write it down. You got the time. If you've got time, we've got the gas law. Room temp is 298 Kelvin. We don't know V2. Oh yeah, the temperature. Yeah, this is where they get you. The temperature goes up 30 degrees, but you got to make sure you can show that in kelvins because it's a different proportion. So there's V1, there's T1. Now be predicting popcorn, hot stuff, getting bigger. So 6.24 should in fact get bigger if it goes up. Now, you can't, your temperature is really not doubling, or that's why we got to use Kelvin on this, because that proportion is really only true number-wise using absolute temperatures using kelvins. Okay, so it did get bigger. All right, what do we got here? Oh yeah, now identify your known, identify your unknown. That is the whole key. Now the thing is liters to liters. Oxygen's a gas, NO2, I believe it says you should ask Miss Levine about. And the thing is, if it is a gas and it's asking and you're going volume to volume, volume to volume, volume ratios is in fact mole ratios. So that's only true. It's not true for solids, not true for liquids, it's only gases. So really it's pretty easy. It's like, oh, 6.5 liters. Well, that is liters of O2. Remember, don't think, drop it down. Liters of O2 to liters of the other gas is the same as a 1 to 2. And so, yeah, if the moles double, the volume of the gas doubles. All right. Okay, oh my gosh, okay, a lot going on here. Now, I think, I could be wrong, but I really haven't seen it. I think this is where we might actually get oxygen gas sometimes. I think this might be a decently efficient way to get it and to get it pure. This potassium chloride, that's a salt. Potassium chlorate, another salt. So this is decomposition. Yeah, what's maybe a little weird is we want to get 5 liters of that oxygen. So the unknown is, well, how much salt? So please identify knowns, identify unknowns. That is everything. So once you've done that, once you've kind of picked out what we're given, where we're going, the whole thing to remember on this is that if this is gas, you can change it to moles. But that's, once again, liters to moles, gas only. What is it else? Some of the other things it gives us here, and yeah, so we've been flying through, but let's take a second here. STP, T is 273 Kelvin, and the pressure is 1 atmosphere. Lots of ways to measure pressures. There's atmospheres, there's these things called kPAs, kilopascals. We do that more in physics too. Kilopascals is really just the same thing as pounds per square inch, PSI. Kilopascals are in fact newtons per square meter. So it's that same force, how much poof, 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 and how much area, how much little space is it hitting? Is it hitting an inch? Is it hitting a meter square? Millimeters of mercury, that's really just the same thing as driving out to the airport, looking at their weather station's barometers and measuring the inches that the liquid metal would rise up the tube. Yeah, so really all of these, it's about, I think this is right, about 14 pounds or so per square inch. That's interesting. There's 14 pounds of air hitting weighing down, settling on, just from the atmosphere, settling on every square inch of your body. That same amount of force would make it go up the barometer about 30 inches or about 76 centimeters. Okay, so once we can do that, so let's do it. Let's do liters to moles. How do you do that? Well, your number of moles it's given. Remember, you're given these equations. So your number of moles would be VP over RT. And I get about a fifth of a mole of oxygen out of that. All right, so then, yeah, then you're like, oh, okay, get it into moles. Now, moles to grams, we can do this. We can rock this out. Okay, moles, write it down, just given. No brain, don't think. Moles of oxygen. Okay, I'm not thinking. Moles of oxygen drop down. Moles of oxygen into the unknown. Then moles of the unknown, potassium chlorate, can go to grams of potassium chlorate. Okay, so moles O2, 3. Moles potassium chlorate, 2. That cancels. That 1 mole of potassium chlorate, goodness, is 122.6. Yeah, I don't know if they gave you that molar mass. I'm running out of space. But gosh, okay. So here's the thing. Multiple choice final, this is why that chemistry final is challenging and good for you and takes a good night's sleep and preparation. A lot of arithmetic. Got about 18 grams. 1 point, please show work, please think. If you understand this problem, I think you kind of understand everything up until now. So thank you for your time. Let's keep going. All right. So let's just take a second here, please, on these gas laws. V, liters. P, oomph. We measure oomph in atmospheres. So volume times pressure equals our sorry, it's annoying. But number of moles, R is what is called the gas law constant. Lots of ways to list it. If really these units, I will say that the significance here is we can measure K, we can measure temperatures, you can measure the amount, you can measure moles, you can measure the volume, you can measure the pressure. That's a measurable amount, so that's really what that value comes from, is making these measurements as gases are in confined space and reacting. And so these are all for gases. And please remember the temperature. You can ask Miss Levine about the gases, but the temperature is in Kelvin. Oh, okay, the gas. If you think of all the gas in the room, we talked about that 14 pounds or 15 pounds, whatever it is, hitting every square inch of your body. You know, that pressure is due to things like oxygen, carbon dioxide, there's nitrogen more than anything. You know, there's hydrogens, heliums, I can't even, you know, there's probably pollution and smog. I mean, there's lots of gases. Water vapor is in there, lots of gases. So our total pressure that we really talk about is just, you know, the summation of all the other gases. So that's really all that this question is they say, okay, here's our total pressure. One of the gases has a pressure of 17. What's the pressure of the other gas? So I think given something like that, you know, that is something most of you could figure out given what's given this. I mean, everybody could say, oh, okay, yeah, I'll get that, Mr. Watterson. I'll subtract 17 and a half from both sides. Subtract that out. And that pressure was listed in millimeters of mercury. And in fact, this gas, oh, they called it, yes, I think this was ammonia, if you can read that. Oh, liquids and solids. This really, it's probably my favorite. I could teach this all year. I love this stuff. Yeah, it's really, I mean, the physics of liquid fluids is fascinating. And this is just a fascinating thing, I think, that when it freezes, remember freezing the waxes, some people may have done it with ice cubes or whatever, but yeah, our temperature flatlines. And so each material has a different point where the temperature flatlines. Another way to say temperature flatlines is kinetic energy. Now this is where it gets really tricky. You could say the kinetic energy of that average kinetic energy of everything in there kind of flatlines. That doesn't really, where it gets confusing is, because a lot of you have learned about kinetic energy, it's not saying the molecules stop moving or anything like that. It's just saying overall, the average kind of levels off. But if you were to look at an individual molecule, it still is obviously kind of, you know, whether you're looking at bond energies or just physical motion, it changes. But anyway, once again, that's just kind of a preview to, please, a lot of you have signed up for your science classes, but really I think physics is fun. Physics is so, okay, moving on. All right, yeah, there's that flat line again. So what did we do here? Oh, if it's liquid up here, it freezes here, it's solid down here, and down there was down there. Okay, what's going on here? Okay, oh yes, dry ice day. And so the thing with the dry ice is it was in the freezer, in the cooler, and it was solid. We brought it out of the cooler, and it sublimed. So we were like, this is not dry ice, but we were kind of in here for like what it was doing in front of our eyes. The room pressure and the room temperatures put us at this solid gas line. Now I think you kind of recognize that this portion in the middle of the phase diagram is in between solid and gas. The critical temperature, and that's a really confusing thing, but it's basically when this stuff gets so hot that the gas just kind of, I don't know, plasma, turns into like a star or something. I don't quite get it. But the critical temperature, when the gas just moves too much, it's labeled critical temperature. 66 was where pressure-wise, where on your P, where on your vertical, where in the Y. The pressure, the way to look at that, this spot here, that is called your triple point. And really, if you could get a material at that spot, it could be melting, and I don't know, it'd be weird. It's not really a cup of ice water, even though that's kind of the same thing. It gets weird, but anyway, the triple point is just where the solid liquid gas, where that intersection of the two lines occurs. You can have all three phases. That is the triple point. Okay, what do we got here? Same kind of thing. Yeah, they show us pressure on the Y, temperature on the X. So that the question here, I forget the question on 67. But the whole thing on these graphs is just knowing where to put your eye, where to put your pencil. So the question is it calls your attention to 0 Celsius. So I just think, okay, I'm on this 0 line here. Now it does have, if you remember, the lines are there. This line and in this line. And anytime you see this, just please label the solids, the liquids, and the gases. Yeah, so they put you at 0. They put you on that. You try to find it. It's not at the 0 point, so that's a little tricky. So to be careful. And they also put you at 30. So I kind of go 0 and 30. Those intersect right there. Yeah, so remember, how did I find that 0? Well, between negative and positive. So, okay, so when they put you there, put you at that spot, you're at the solid and liquid line. Okay, what do we got here? Okay, we got nitrogen. Oh, the whole thing here is like, this isn't a reaction, it's nitrogen and nitrogen. It's nitrogen, liquid nitrogen. That's fun to play with if you've ever got the opportunity to see. Hope maybe you have. But yeah, it's kind of like the dry ice in the sense that we open up the cooler, room, instantly. The room provides the E. The room provides enough heat energy to basically make it boil. Because remember, nitrogen is in the room, it's a gas. Inside a fancy cooler, you can make it be a liquid. Endothermic, that is adding. So yeah, really another way to think of endothermic on that is that your energy, your E is added. Your E is an ingredient. Your E is a reactant. You can't, yeah, technically boiling is vaporizing, that's fair. So, yeah, and so what does that mean? I'm looking at that, and that to me is true, true, and true. So yes, all of these, choice E is all of those are true. Yeah, just on a side note, most of us know exo as giving off energy. If that is the case, if you're making it, if you're producing it, your energy becomes a product. If it's exo given off. Burning the Bunsen burner, yes. Okay. All right, so let's look at some of these. Please, I just think if I did this, do I have to put heat in or not? So liquid, think water. Water's fair. Think of the room. We put some water. Got it. And another way to think of it is what happens. These guys are floating around. Then like, wahoo, boiling, moving, jumping out. So that had to put energy in. Are you speeding them up or slowing them down? You're slowing them down. They're like, woohoo, moving around, then real rigid and solid. I had to take the energy out. So these definitions are from the perspective of the molecules. That's the hard part. Okay, but think, solid to liquid, I had to speed them up. You got to give it a kick. You got to oomph. You got to put something into it to speed it up. Solid to gas, got to speed it up. Got to put something into it. Got to get it to go. So there we go. All right. Okay, why do things boil? A few reasons, a couple ways. You can heat it up and woohoo, woohoo. These guys start, everyone's kind of seen this, hopefully. Bubbling, water. Woohoo. That, woohoo, that is called vapor pressure. All right. The water vaporizes and applies a pressure. It's called vapor pressure. Now, I think you've seen this, but we can boil it without making the guys go woohoo. And it has to do with what the air is doing. All right, and so this air, remember we talked about the 14, 15 pounds setting on everything. That is the air pressure. Sometimes it's called atmospheric pressure, air pressure, surrounding pressure. But I think common sense looking at this, if you look at the pushing down and the woohoos, if you look at the and the woohoos, when the woohoos win, it boils. Or more specifically, the threshold is when they're equal. So when your vapor pressure equals your atmospheric pressure, when these things are in fact equal, then that is when you can get it to woohoo. That is when you can get it to go. And so yeah, going back to what we did in class, we can change, if we change this, lower this, then that is easier. And oftentimes the room temperature was enough to make it do that. So boiling is when atmospheric and vapor pressure are equal. Sorry. Okay, what do we got here? Oh, goodness gracious, specific heat. Okay. Yes, I'm going to cook something. I don't want to change its phase. I just want to cook it. I just want to make it hot. I just want to make 1 gram of it, a little tiny bit, go up a little tiny bit. All right, so it's basically just reduce that ratio. Here's how much heat it takes to cook 43 grams by a factor of 30. All right, so here, be careful here. This is where I see this mistake, is that really should be parentheses. So yeah, a few ways to do it. Either use parentheses. A lot of times I just hit the divide key twice, but that is the most common mistake on these. A lot of people can plug and chug with the best of them. Given formulas, given variables, just go at it. Yeah, because remember the temperature here is really how much it changed, right, how much you're increasing it by. So yeah, choice C on that. But yeah, you're just reducing that ratio, how much energy to get it down to per gram per degree, per gram per degree. Okay. All right, yeah, our famous graph again, our flat line. The thing to remember here, when it's flatlining, there is an amount of heat that changes, and those values are reported per gram. So if we have 10 grams, we multiply it by 10. We got 5 grams, multiply it by 5, etc. And that, so it does, even though the flat line is there, there's no delta T, it still takes some energy to make it go. Now, the other parts is the slanted portions. There is a delta T. And that is what we just kind of went through with the specific heats is really what determines the energy involved with the slanted part. And the values of the specific heat are reported per gram, so that's why we take that mass into account. Just more mass is more calories. More mass is more energy. Now, what you have to decide here is, and I think this one was water, so that's usually what we see. Our Q1 is the thing that they make us decide upon is which delta H to pick. And you have to decide, is this steam or ice? Or is it condensing or freezing? It's freezing is 0. 0 was there. Freezing they decided to call fusion. Alright, so we got 10 grams of the stuff. Delta H fusion was 334. So this would be 334 times 10. Q2 was, now the delta T is 20. It goes down 20. Still our same 10 gram sample. And then you have to decide which specific heat. At negative, in this, it's ice. It's ice down there. So the hard part is picking out the correct specific heat. I get 412. You add these together. I believe that was choice B. All right, we're getting there. Okay, I love this. I love water. You see water, please add polar charges on each side. Oxygen's negative, water's positive. Roll the balloon on your head and watch the water move. Okay. Okay. annoying. What holds the water together? Well, really, it's this. Partial positive, that is really what we say hold it together. But there are other electrons moving around. There's really electrons moving around in everything. A guy named Fritz London said electrons are dispersed in everything, so everything has those small charges allowing it to stick together. The acetone, if you remember, said that, but the idea, the forces get stronger, and that was why we were kind of playing with it. Water had a lot of these stronger forces associated with it. You could call those dipole-dipole. This partial charge to this partial charge. So that's what dipole is. It's just between the partial charges. A very specific one that is in my favorite is called a hydrogen bond. And that's really what my is a hydrogen bond. And those, yeah, that made water a little bit stronger. Stronger than the acetone, relatively strong. So yeah, the choice was A because really it said CF4 is a nonpolar. Now, how did you know that? If you were to draw it, you would not include these partial charges on it. That was tough to recognize this. I think that was tough to recognize CF4 as nonpolar. But really, two nonmetals. It's kind of like methane or something like that in terms of its structure. Okay. Yes, so going back to, we could smell it. We just opened up it. Woo! Opened up the acetone. It's gone. A lot of times my daughter, she loves to paint her fingernails. She'll leave the bottle of acetone open, come downstairs, play, come back up. Oh, it's gone. Yes. So what does faster mean? Faster really means easier in the room. What does easier mean? Easier means it's easier to boil. Easier means it's easier to vaporize. What does easier mean? You know, remember this is the vapor pressure. Escaping. So it's easier to separate. It's easier to separate those molecules from each other. Yeah, so choice B on that one. Okay, doing well. Choice B on that one, sorry. Let me see, how am I doing? Am I still on the screen? Okay, moving along. What do we got? Oh yeah, hopefully you remember putting our little paper clip on the water. It really didn't float. I mean, the paper clip would sink very, I mean, if you just put it in there, it's made of iron. It's like a stinking nail. So it's not floating. It's not a density issue. What did you do? You were only just, and it took some time. I don't know, I got it to happen for a lot of you. But yeah, it just sat there. It just sat because the water has such high surface tension. It's kind of unique. It would sink, but you can set on the surface. That's the whole key with that one. All right. Ooh, gosh, getting close. This is another. I love water, so this is favorite topics. Yeah, salad dressing. Hopefully, you got some chance to kind of play with this. Our oil. We also probably in class you use like the gasoline, the fuel oil, that cyclohexane. Another way to think of that. All right. So with these solutions, water is our universal solvent. Let's see, what do we got here? We want to figure out the moles, and we have to figure out the liters. So those are really the steps. So maybe step one, okay, I got this as my given. Not even going to think. Grams of KOH, drop it down. Mole KOH. A full mole, oh gosh, tedious arithmetic. Yes, here it is. Okay. what do we got here? If I do potassium is 39, oxygen is a 16, hydrogen is 1. Yeah, that's where I got the 56. So molar mass, so yeah, so 14 grams, 14 is just a small fraction of that. Yeah, okay, it's a fourth. Come on, everybody knows 14 is 1/4 of 56.1. So I have a quarter of a mole. I don't have a full liter though. I only have 150 milliliters. 150 milliliters. Well, don't think milliliters, liters. And this is where just measuring stuff. You know, if you just remember, 150 milliliters. Go back to that beaker picture. Very first thing. It really does help get that sense of scale. So yeah, so not a full liter. So moles, my ratio of moles per liter, big M, that's concentration. That is really everything that we use to try to figure out. Sorry, I need to get myself situated here. Is that better? Okay, moving along. All right, what do we got here? Another moles per liter one. So yes, same kind of dealy, Bob. Find your moles. Okay, yes. This one you had to solve for the moles. So yeah, big M you're given, liters you're given. Bump that over to the other side. Nice, very nice. Okay, moving on. 78, 79. Okay, those charts, hopefully you've seen kind of a chart like this. What you really want to try to do is, first of all, call your attention to the chemical, the line. Now what that line is, that's really the saturation. That's really how many grams of that junk you can dump in 100 grams of water. So please read your y-axis, read your x-axis. That's very key on these. So I think the question was, how much of the potassium chloride can fit in water at like 80 degrees Celsius. So if you kind of come up here, it's like, all right, I get to 8, I hit the line there. I'm going to come over. That ends up telling me that I can put 50 grams of potassium chloride in water at 8. Now, how much water? 100 grams of water. So the question was how much would fit in 50 grams of water. Well, if it's 50 grams of water, then I'm only can squeeze in 25 grams is all that will dissolve. Now let's try C. Okay. So read your axes. That's my best advice for you on any of this. Okay, moving along, same kind of thing. What do they want us to look at here? They call my eye to a temperature of 90. A temperature of 90. Okay, so you have no choice other than to look at the list. So it's really 4 questions. They give me this stuff called ammonium chloride, and that kind of goes like that. They'll give me another stuff called potassium chlorate, and that kind of goes like that. They give me this other stuff called potassium chloride, and that kind of goes like that. And they give me some other stuff called, oh, we know this one. This is my popcorn salt. Sodium chloride, and it kind of goes like that. So I have to pick the most soluble one. All right, very nice. Okay, same kind of graph here. So yeah, being able to read your graphs, it certainly helps. It's a skill we try to emphasize. What are they doing on 81? I forget. They call my attention to 50 degrees Celsius, so I kind of find that. They call my attention to potassium chlorate, so I look for that. And they say if you have 20 grams, well, what a coincidence. If I have 20, that's the saturate, it's saturated. So remember, on the line, really, if you're on the line, that really means you've dumped it all. Think of our golf balls, please. You know, I've been trying to keep those solutions saturated. And really, as that salt dissolves, more and more the golf ball, remember, would float. So saturate is just how much of that salt can I dump in there. So yeah, on the line, please, on the line is your saturation. That is how much you can dump in there. Okay, so what does the question say? The question says you got to think, am I going to move this way? And I think it does. The temperature says you increase. If you increase temperature and you still keep your 20 grams in, well, now I got room. I can go up. I could get it back. I could dump in like 30 or something to get up there. So really, if I heat it up, I got more room. It becomes unsaturated. And really, just kind of, you know, conversely, it's easy, I think, to think about it. If you go back, if you cool yourself down, you're above the line, or you can only hold like, now you're like down to like 10 you can only hold. So if you cool it down, and I don't know if you ever did like crystals, or just think about it. If you heat it up, you can put more salt in. If you cool it down, you can put less salt in. That's all it's saying. So, okay. Yeah. Maybe I need one. I'm losing my voice. No, I'm kidding. I don't like soda's so bad for you. It's not really because of the carbonation. It's because of the sugar, or the fake sugar. Anyway, everybody's opened a can of soda. That's what this question is all about. And the question says, what can we do to the soda to keep it fizzy? To keep it ready to fizz, I should say, or to keep the gas in there. Well, if I have my soda and I stir and shake it, what's that going to do? Oh, if I stir it up and shake it, gas gone. So that's not good. If I open it up, woo, gas gone. All right, leaving an open can of soda, that's not going to do it. Why? Because remember, the can is pressurized, so when you open it up, the pressure becomes equalized with the atmosphere. That's a lower pressure. If I put my soda in, what do they do? I mean, what's a nice, refreshing Coca-Cola, part of American culture? I'd like to give the world a Coke that's been refrigerated. All right. Now, here, this is probably, okay, 6 questions here. Relatively very, very abstract topic, quite honestly. Energy is really tough. That is also another, next year, physics. That's really, I think, a theme of the class, is studying energy. So any introduction you get in this year is going to very, very much help. Now, really, the questions on these, it's very simple, because all the work's been done. You just have to understand the definitions. We talk about energy changes as being endo or exothermic in this class. Positives, putting heat in, so positive delta H's are endothermic. So that means you're adding it. You could like think of the energy, the heat, as a reactant over here. So you're given this value, and that is the heat required to make, boom, to make it go, to make it happen. But those values are listed for the ratios in this balanced equation. They're listed for that. They're listed for 1 mole of silicone. They're listed for 2 moles of chlorine, 1 mole. So the question is you don't have exactly what the listing is. You only have 106 grams. Okay, no brain, don't think. Grams, drop it down. Grams, drop it down, change it to moles. When you do that, oh gosh, this is so dirty. A little bit of side work here. 2 chlorines. Add that together, that's 71. So a full mole of chlorine. So I have more than a mole. If I got more than a mole, I don't quite have 2 moles though. So it's going to be And so that's what's going on here is you know this number is your mole to joule conversion. So that's what's weird is you're really doing a mole to kilojoules, and that is what those delta H values do, is they give you the mole to kilojoule for that reaction. So those values have been determined experimentally, they're listed on tables, but please remember they're listed for the reaction for the balanced reaction. So choice D. So I just think, okay, that's how much it takes. Do I have what that recipe prescribes? Figure out what fraction or what ratio of a mole you have. Then you can figure out how the relative amount of energy. Okay. Gosh darn it. I believe you got the good picture of that. Maybe not. Okay, keep going here. Same kind of idea here on this one. This is going to be a grams, and you're given, once again, you're given that delta H. But please remember that delta H amount of kilojoules is for 1 mole. A mole of methane is a carbon and a mole of methane is 16. So if a mole of methane, a mole of natural gas is 16, and yeah, I'm forgetting the question, sorry. A mole of gas is 16. So this is, yeah, a mole of gas was 16, so I have a fraction of that required to generate 250 kilojoules. So yeah, once again, I think this was that delta H for the reaction. I got a fraction of that amount of energy required, so I'm going to need a fraction of a mole to get that to happen. That is that lighting your Bunsen burner? Please look at that for a second. So what is lighting your Bunsen burner? That is giving off energy. So that should be exothermic. Okay, yes. Ooh, what a coincidence. They are going to have us look at a graph of burning this thing up. Now think about what you do. Okay, so we get to go back and start cooking stuff. All right, get to burn something up. You got to, the first thing you guys do when you get back there, light your Bunsen burner, is you try to spark it up. All right, on this graph, if you just turn on the gas, you know what? It eventually would react with oxygen, but it's just very, very slow. We can get it to happen a lot quicker by providing the activation energy, by providing that spark. And that is this hump on this energy graph. So think of lighting your Bunsen burner. It really helps. Okay. So you turn on the gas, you turn it on, and think of, this is your reactants right here. So this is your methane, these are your reactants. What was our reactants in lighting the Bunsen burner? Well, it's methane and oxygen. Okay. When we burn up the Bunsen, what do we get? And this is combustion. Oh yeah, don't forget that. What's coming out as a result as it burns? What is our products? Well, our products are represented down here after the certain amount of time. Now, the thing is, water and carbon dioxide have less energy available than gas and oxygen. That's why, that's really kind of, we can't burn up water and carbon dioxide. It'd be great if we could, but our products have less energy than our reactants. Okay, and then what's this part here? This kind of downward exothermic, this release of energy you're looking at. This is like the exothermic part of it. It's very burning. That's the heat you feel. That's the reason you kind of like have fun in a chemistry class. Okay, So let's look at this. So what are some of the choices here? 85, what was the question? Gosh, forgetting. Was 85 says which letter, which is the delta H? So yeah, this is it. It's the delta H. Here, this is the easiest way to remember it. If you take your products, so your products that you got over here, your products, and you subtract that from the energy of your reactants, that is what we like to call our change in energy. A lot of times that's heat energy. In this case, that would be very negative. There's less energy in no carbon dioxide and water than there is in your reactants. So in this case, it's losing energy. It's very negative. Energy goes down as you look at that forward reaction. Okay, so what was the question on 85? What is the delta H? Well, the delta H is this. It's that products minus reactants. It's this right here. That right there. Let's get a better one. This right here. That is your change, your delta, your triangle in heat. And it goes down. That's why it's negative. That's why it's exothermic. So yeah, 85, that would be choice C. It's kind of weird. It's not the line. Yeah, I had trouble kind of looking at the way it was labeled. Be careful. Choice C, it's this space here. It's just kind of misleading. It's choice C. Choice C on that. Okay, 86, really looking at the same graph. What's going on here? 86 is what's the potential energy of your reactants. So here was your reactants. Yeah, so right there, this amount, that amount right there. 87 was saying, well, what if you went backwards? So 87 was all about going in reverse. And if you go in reverse, that would be the opposite of exothermic. All right, going. And then 88, what was 88? 88 was saying, oh yes, the spark. All right, this is a big deal in biology. Biological enzymes, catalysts, allow us to stay alive because they lower the spark required. They lower this bump. They lower that piece right there. They lower the activation energy. The energy of activation is lower with an enzyme, is lower with a catalyst. It just provides an environment where the flint sparkers make that easier. There's a lot of ways to get it to spark. The flint provides an environment where that gas sticks to it. The oxygen is right there. It just provides that right environment for that reaction to start going. So catalysts lower this. They make that activation energy get smaller and smaller. All right, my favorite. Getting close to the end, you guys. You're rocking and rolling if you're still with me here. Now, it's text to text, book to book, class to class, arguably. This is water plus hydrogen ion. It kind of leads to the idea that we still struggle with how to represent what water is and how to describe these color changes with acid-base indicators. But yeah, the notations, H plus, H3O, same thing. A few ways to, I'm going to do 89 a different way here in a second. You did look at some problems solved this way with KW, given that, and I guess the way you kind of set it up, it's a calculator exercise like a lot of the stuff we do. But please remember, keep that in parentheses, use your EE key on the denominator there. That's what really makes it happen. So yeah, there you go for 89. Can you see that? All right, now a different way, same thing here on 89. And maybe this is a little bit more involved, but yeah, let's just do it. So your given concentration of the hydrogen. that extra hydrogen in the water. That's really what it is. That's what acids are. Extra hydrogen ions in the water. Okay, so that makes sense. pH 3, that's an acid. It's an acid at pH 3 because it has the extra hydrogen in the water. Okay, that's not the question. The question was how much hydroxide, because it's water, so there's everything in there. It's still hydrogen, still hydroxide. So we got my acid. It's in water, so it has a POH. Remember, acid, the POH of acids is above 7, where pH, we always say is below 7. So if I know the POH, remember these equations, please remember given our favorite thing with the formulas. It's really, can I find my inverse log button? Your inverse log button is the same as 10 to the exponent. Look at your acid-base quiz. For a lot of us, this was a question on there, and there was, a lot of you found some shortcuts and different ways to do it. But yeah, I don't know, sometimes the KW method works, but this method also works to arrive at the same answer. Okay, what are we given? We're given molarity of OH. What can we do with that? Well, it's a base. I can plug that value into my calculator. By now, if you've gotten this far, you're good with your EE key. You're good with your exponent key. Okay, so that makes sense. So this is a base. The POH is below 7. That's the same thing as saying the pH is above 7. It's a base. Okay, that's true for bases. Let's just finish it up. The pH plus that 4.5 or so means that the pH, yes, that makes total sense to me. Base has pH. And remember, this is all just kind of a mathematical way to establish that things change color in acids and bases, and we can predict it using these values, using these concentrations. So, kind of what to remember about an acid. Is an acid going to make hydrogen? Yes. Yay. Very happy. Is an acid pH less than 7? Yay. Do they make hydrogen? Yay. Because remember, hydrogen, this is weird. That's why maybe I love the topic, is because it's still, smartest people on the planet still argue about it. H plus is a hydrogen ion. H plus is also called a proton. A hydrogen H plus ion is also called, this is called hydronium, or extra hydrogen on water. So really all three of those things are the same thing. Hydrogen ions, protons in solution, protons in solution, protons in aqueous solution, H3O. That's all the same thing, but yes, all different ways to say my indicator, my cabbage juice turns red. Blue to red, acid. Okay. I think we're at the end. I can't wait. You guys go have a party or something, or not a party, but take a break, get some good night's rest, and then you can knock it out tomorrow or whenever on your final exam. Go, Ladue, go, Ladue. Okay. Like I said, people talk about this at graduation. It's a good experience. Okay, we're given the okay, I remember this one. What's in there? Okay, yeah, this is kind of funny notation-wise, but potassium hydroxide makes potassium and hydroxide. But remember, this is the whole thing. It's everybody's favorite. AQ. What is AQ? AQ. It's water. It's in solution. It's aqueous. All right, now this is kind of a fun place to stop the year, but water is very special. A glass of water, if you were to just go around and say, okay, here's my water, and we all say, yes, first day of school, what is water? Everybody told me H2O. And I would say, last day of school, what's water? H2O. Wrong. It's water. It is H2O, but it's also that, and it's also that. Okay, you get 10 to the minus 7th moles per liter of those floating around. That's why water is pH 7. So anyway, what is water? Water is some of this, some of this, some of this. You drop salt. I'm going to take some salt, Mr. Watterson, and drop it in the water. Drop, 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 drop. Drop some salt. Drop some salt in the water. That's this, and it's this. So it's kind of a weird way the questions, but that's in there, that's in there, that's in my solution, that's in my solution, that's in my solution. So it's kind of weird, but it's just really asking you what is in the solution. Choice D. All right, congratulations. If you made it through my videos, you really deserve to do well tomorrow. Thank you for watching, or whenever your final is. Good luck, class. Good luck, Ladue. We like you. Thank you for listening.